Hi there, my name's Isaac. I'm a tutor at CWI, and today I figured I'd talk about work and energy and potential energy, kinetic energy, and conservation of energy. So, one thing that you may have noticed so far is that we've had to use components, usually in two dimensions in this course, to get vectors into two different unitary directions. That way we can add things in like directions. And we've noticed that can be kind of tricky. It can take longer. It can take more energy to do a problem when we have to break it into its components. And so the beautiful thing about energy and work and potential energy is that they are scalar. So what this means is that all this stuff that we've learned about directionality and having to figure out things in orthogonal directions, we can now kind of put that aside, and although it'll always pop up, it's still going to pop up, but it's important to know when using energy might be simpler. So just as an example, let's go ahead and say, well, let's talk about potential energy. So with potential energy, you're going to reference a certain line, and you're going to call that the potential equals zero line. Usually I pick that to be the ground, because usually nothing's going to go below the ground. So if something is on that horizontal line, gravitationally it will have no potential energy. There's other things that can give potential energy, like springs, but in this case we're just looking at gravitational potential energy. Well, what if I grab this ball and I pick it up and I put it up here? So I've gone some vertical distance, we'll call it h, and now my mass is up here. So it started down here, and I had zero potential energy. Then I moved it up there, and in doing so, I did work. Okay, I did work to push it up there in the gravitational field, and the amount of work I did, and thus the amount of potential energy we've given the ball, is or potential energy due to gravity, is equal to mgh, where h is the vertical distance that I move the ball. For example, if I move the ball this way, my potential energy due to gravity is mgh. If I move my ball up this way, the potential energy is still mgh. The reason being is because when I'm moving it horizontally, there's no acceleration, there's no force when we move in this direction, which is of course why trajectories are parabolic, is because there's no force in the x direction. And thus, in a perfect world, moving something in the x direction on Earth gives no potential energy and requires no work. So there's no opposing force. So let's say that we go ahead and we want to drop this ball now. And we want to see how fast it's going when it hits the ground. So, and we'll have to do kinetic energy as well to get here. So we start off with the ball up here, and we drop the ball. And so we're going to go ahead and denote our beginning and our end. And I like to do it this way. I like to say there's some energy initial up here, and then there's some energy final once we've hit the ground. And the beauty of the conservation of energy is that in a system without loss, so in other words, we got no air resistance, no drag, no friction, what we're going to end up seeing is that the energy that the system starts with in a closed system is also the energy that the system ends with. So energy initial equals energy final. I suppose you could write this as a summation, because sometimes there's going to be more, there's probably usually going to be more than one kind of energy. But in this case, we're starting with all potential, and then when we hit the ground, okay, now here's a trick. Just like with trajectories, math doesn't understand what the ground is. A parabola goes off to infinity. It's up to us to tell it the boundary conditions on where to stop. But what you're going to find is when we drop this ball, it's going to start gaining velocity with respect to 9.8 meters per second squared acceleration. And so it's going to be gaining kinetic energy. But you'll notice as we get closer and closer to this potential equals zero line, we're going to have no potential energy once we get there. And so we'll notice is that our energy initial, if the ball starts at rest up here, is simply the potential energy due to gravity. And once we're at the final position, all of our energy final is now just the kinetic energy final. Now, we know that potential energy due to the gravitational field is mgh, that's the definition. And we've learned that kinetic energy is equal to 1/2 mass times velocity final squared in this case. And so let's go ahead and give ourselves, well actually let's not focus too much on the numbers because, so in other words, if I gave you the mass and the height off the ground, I could ask you what's the velocity the instant before it hits the ground. Now of course once it hits the ground, energy from the ball is going to be transferred into the ground, and all of the potential energy from up here will eventually go into the ground. But we're ignoring that and saying, what is the velocity of the ball the very instant before it hits the ground? And then we can use conservation of energy. Alright, so that's, and you might notice that the answer would be absolutely no different if we put the ball on a parabolic trajectory. We would in fact still have the same velocity in the y direction when we hit the ground. Of course, the x direction is going to have its own velocity that's going to be constant the whole time. So you'd have to include that using Pythagorean's theorem. But the y component of velocity is going to be the same because it's dropped the same amount, therefore it's accelerated the same amount in that direction. So let's take a look at some other forms of energy. For example, spring energy. And let's go ahead and look at the definition of work as well. So in Physics 211, the primary definition of work is going to be the integral of the force dotted with the infinitesimal segment. And so what this means is that if you imagine that if you're moving something from, say, here to here, what we're doing is we're looking at every infinitesimal dr, or some radius, and then we're going to look at the force that's being applied at that given point in time. And so you'd notice that if the force changed as we went throughout this segment, then we would have to integrate, because force in this case would be dependent on position, or where we're at. But let's kind of simplify it for now and get to a more easy to use and look at expression. So I want you to imagine that, say I have force in this direction, and my force is constant through a displacement, and we'll call that displacement r. Now if my force is constant at every point throughout this displacement, then what that means is that my force is not dependent on my position. In other words, the force is the same at every infinitesimal point. And you'll remember that with constants, so in other words, force is not, in this case, a function of position. Therefore, it's a constant. So we can pull it out front, and we end up with work equals F integral of dr. There's still a cosine theta in here because of the dot product, right? F dot dr is F dr cosine theta. But cosine theta is also not dependent on r in this case. So the integral of dr is just r, so we end up with work equals F r cosine theta, where F is the constant force, r is the displacement, and the angle theta is the angle between the displacement and the force that is applied. So I hope this isn't confusing. I'm just drawing at different instances of displacement that we have the same force going on. So this is the formula if force is constant, and so that can be useful. Let's look at it, something where force is not constant. For example, a spring. So let's say that we have a spring, and we're going to start with like a box here, or something like this in a wall, and we're going to push that box and compress the spring. Now, this is a form of potential energy, because you'll notice that if we were to let go of the box, the spring would seek equilibrium, where it would no longer be being compressed. And so we know that Hooke's law tells us that, for example, if this is some displacement in x, and this is the original position of the spring, we know that Hooke's law tells us that the force caused by a spring is equal to K, which is a constant, times the amount that you've compressed the spring or extended the spring. And usually there's a minus sign here, purely for notation, to remind you that whichever way you're applying a force, the spring is always going to be resisting your force. But this is just for notation, so let's not worry about it. It's just always going to be pushing in the opposite direction of how you're trying to push it. So I know my force, and it is a function of its displacement, right? In other words, the force, when I push it in a little bit, will be less than the force when I displace the spring a lot. And so in this case, we can't pull force out of our displacement integral, because force is a function of displacement. So let's go ahead and write this in here. Work equals the integral of force, which in this case it's the force of a spring, and you'll notice it's a function of x. And if dr is always in the x direction, which in this case it is, we can just call it dx. So f dot dx. Now, let's say that we are applying our force. Well, the spring's always going to apply its force in this direction, right? The x direction. So cosine of theta, for example, here the spring's pointing this way, and the angle of from the force and the displacement is just 0 degrees. Cosine of 0 is 1. And so now at this point, we can do this integral by plugging in the force as a function of x. So work equals the integral of kx, and of course x is just delta x, where you started to where you finished, dx. And we're going to compress it from some 0 to x. So in other words, when the spring's uncompressed, to where we finish is 0 to x. That's how we're going to define it. And of course, k doesn't get acted on by the integral because it's a constant. So the integral of x is x squared over 2. The k hangs around, and then we'll evaluate it from 0 to x, which if you work through it is simply going to be 1/2 kx squared. And so where x is actually delta x, I'm just writing it as x. It's from where we started at the 0 force of the spring to wherever we're at. So the work put into this, you remember how I was telling you that when you lift a ball off the ground, you're putting work into it that is equal to the potential energy it will have once it's up there. So in other words, we put work into it to get it up there. Now that it's up there, it has all that work still stored inside of it, and it's done through the gravitational field. In this case, we pushed the spring, we compressed it, and all that work that we put into the spring due to the conservation of energy is still in the spring. And this is the formula for how much potential energy is in the spring. So work is kind of like, it's got this funny relation with potential energy where you put work in and you give the system potential energy. So even though this is the work we put in, I can now also say that the potential energy due to the displacement of a spring is equal to 1/2 kx squared. And so I think I've probably talked for long enough on this. It's getting to be a longer video. I hope this helps, and we'll definitely do some example problems. Remember, the energy you put into a system is the energy you get out, especially in a closed system, but we'll look at friction and other things down the line a little bit. All right, I hope this was helpful, and I'll see you next time.